Okay, but I like this topic. I like all of these topics. But we've been talking about how fast a reaction occurs. That's called reaction kinetics. But kind of behind the scenes of how fast it occurs is this concept of reaction mechanisms. So a reaction mechanism is kind of like a script. You start at the beginning of the script and you go to the end of the script. At the end of the script, you have your overall chemical reaction. To me, kind of like these elementary steps, kind of behind the scenes, all add up to the reaction of interest. They're what we say a pathway to get from point A to point B, A being your reactants and B being your products. And we're actually going to apply that. Remember with Hess's law, we actually said if you can add these baby equations together and get an overall reaction of interest, then the enthalpies can sum together to get the overall enthalpy of the reaction. So to me, we're going to kind of work on that premise where we're basically adding, in this case, we're adding elementary steps behind the scenes. Now, do we see those elementary steps? Do we see them occurring? Bah. Do we have evidence that they're occurring? Yes. Okay. Now, before I get too much farther, one of the things, and I said that I would revisit this, I'm going to say we have two reactants, A and B, and these are the stoichiometric coefficients going to form some product or products. We could write the rate law expression. So your reaction rate is equal to the rate law constant K times the molar concentration of each of the reactants raised to the reaction order. I'll just call them M and N for now. And I told you that you cannot get to those reaction orders from the stoichiometric coefficients, didn't I? And that is totally true. This is your overall rate law expression. Okay? How do you get to M and N? Experimentation, that's it. All right. Well, I'm going to change it up a little bit. So those kind of things behind the scenes, those elementary steps, okay, or I should say those steps behind the scenes are called elementary steps. Okay, so you have a reaction of interest. You have step, 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 reaction of interest, okay? The elementary steps add together to make over the overall reaction of interest. Makes sense? And so collectively, the set of elementary steps are called the mechanism by which the reaction occurs. Okay, little baby elementary steps. They're adorable. Well, this term molecularity applies only to the elementary steps. Molecularity, like the slide says, is the number of participating particles in a given elementary step. So molecularity only applies to elementary steps. Molecularity is applying to the reactants for an elementary step, okay, not the products. Molecularity is actually counting the particles. Okay. So we have a couple of options with regard to molecularity. We have uni, meaning mono, meaning one, monomolecularity, uni, like a unicycle, a one wheel. Unimolecular means that elementary step only has one of those particles. Okay? Bicycle, instead of a unicycle, bimolecular, and again, these are molecularity terms applying only to elementary steps, right? Ter or tri, I think we'd go with ter. Ter or tri-molecular means that actually you have three of that particular particle on the reactant side proceeding to form product for an elementary step, part of an overall mechanism. So examples of unimolecular elementary steps would be A goes to form B, or A goes to form B plus C. A is unimolecular. Bimolecular could look like this, where we have A plus B goes to form C. 2 parts of A goes to form B. You know, I guess to me the second and third one are the same thing. The trimolecular or the termolecular elementary step. Now I want you to kind of put this in the back of your mind because it's important when you're actually trying to come up with a mechanism by which an overall reaction of interest is occurring. Termolecular is not very likely. Do you remember was it 3? I think it was 3, or was it 4 different things that go to make our reaction rate? And one of them is they need to collide. So with termolecular, you are saying that in order for reactants to proceed to form products, you need to have 3 particles successfully unite. Okay? Now I'm not saying that we don't have overall chemical reactions that occur where you have 3 reactants. That happens. But instead of happening in one fell swoop, usually what happens is something like this. Okay? If it looks like it's termolecular, probably it's 2 bimolecular sort of things happening. That's a script is what I call it. So for instance, we could have 2 B particles get together to form D, and then we could have an A introduced to connect with your D that you formed from the first elementary step to form your product of interest. Just for kicks, I'm going to go ahead and draw a line under those 2, and we're going to add those 2 potential elementary steps. That's what I'm trying to describe here. That'd be first elementary step, second elementary step, line. Okay, we've done this before. We basically, let's see, I can do it a couple different ways, but do you guys remember this? What can we do with D? Because it exists as 1D on the product side, 1D on the reactant side.
Do they cancel each other out?
They do cancel each other out, exactly. Okay, now I'm going to bring down A plus 2B goes to form C. So that's our net equation. D actually, is this right? I think it is. D actually is what we're going to later call an intermediate. Is it important? Yeah. Does it form? Yeah. Is it isolatable? I don't know. Okay. But is it in your overall reaction of interest? No. It's kind of there for a fleeting second. But do you see where actually, as I've written them, we have bimolecular, bimolecular. Up there at the top, that'd be termolecular. Probably not very likely. Okay? But also, do you see where what I came up with 2 elementary steps is the same thing, the overall reaction of interest. That's exactly how mechanisms work. Okay? All right. So a rate equation that I wrote up here, rate equation, we've been talking about rate law expressions, rate equations, same thing. Okay, you can't get to these reaction orders from the stoichiometry. You just can't. You cannot. Thou shalt not. Okay. But if you were talking about the rate law expression, how do I say this? I was thinking about this today. I'm like, well, maybe they don't know that. So I'm going to go back to my behind the scenes. I have elementary step 1, elementary step 2. I draw a line. I have a reaction of interest. We can write rate law expressions for an elementary step 1 and an elementary step 2. Guess what? If it's an elementary step, by golly, we can use the stoichiometric coefficients as their reaction orders. It's so fun. Only if it's an elementary step. Okay? And, yeah. Because does this not make sense that if you're writing a script and you have 2 elementary steps to go to make your reaction of interest, there's going to be a rate associated with this step, there's going to be a rate associated with this step. That's true. You can write rate law expressions for the individual elementary steps, and then you will use molecularity, which is the same thing as their stoichiometric coefficients. All right, so let's see what this looks like. Only if, these are all elementary steps. If this is an elementary step, we can write the rate law expression for this elementary step like this. Rate is equal to K times the molar concentration of the reactant raised to its reaction order. Stoichiometric coefficient associated with A is 1. That's its reaction order. Why? Because this is an elementary step. Okay? Just do another one. That was unimolecular. This is an example of a bimolecular. Okay? And if it's an elementary step, I can come up with reaction order for A and B. What would they be if we can use stoichiometry to be the reaction orders? They're 1, exactly. So the little rate law expression for this elementary step looks like this. Rate is equal to the rate law constant K times the molar concentration of the reactants raised to the first power, because their reaction order is 1 from their stoichiometry, because it's an elementary step. You see why this just drives me nuts, though? Because only reason we can do this is because these are elementary steps. Okay, let's do another one. Another bimolecular. Bimolecular. Okay, only one reactant. So the rate's going to be equal to K times the molar concentration of A raised to its reaction order. So what's its reaction order if this is an elementary step? It is 2. Exactly. Okay, that only works because they're elementary steps. You're like, I wish it worked for overall reactions of interest, but no. Okay. I was thinking of this, if you're like, hey, you guys watched the, those shows where they go out into factory and they show you how it's made? Okay, I think those are so interesting. So if you're watching one of those, for instance, if, how do I say, pick something like, I don't know, I guess if you're making taffy, I'm hungry. Okay, so the whole taffy thing might go something like this, where you have different steps that make your wrapped taffy. And so kind of adding the ingredients takes a certain amount of time. But what I think of taffy, like homemade taffy, you have to pull it, right? So the step in the factory where you have to go like this, where you have to basically mechanically pull it, taffy, that takes a long time. Okay, so you could break it up into steps. You could say, well, mixing it, that doesn't take too long. Okay, stirring it, not too long, but this takes a long time. And then we'll just assume that it kind of, you can get it in the shape and you can wrap it pretty quickly. Well, this is the rate determining step for making your taffy. How long does it take to go from sugar and water and food coloring to a piece of taffy? Well, it's kind of, this is so slow that this actually determines how long it's the overall rate determining step. I also kind of liken it to if you're trying to get out the door and you're a member of 5, you have a family of 5. You have somebody that's a little bit slower than everybody else. So collectively, how are you going to get out the door? Well, it depends on that one person. That's your rate determining get out the door person. Okay? So that's the slowest step, is your rate determining step. So how fast, can I get out the door? Well, it all depends upon usually me, probably. And I would be the rate determining step. So again, it just, how long does it take to make taffy? Well, it probably depends upon this. How long does it take for me to get out the door? Our family, collectively, probably depends on me. So the rate determining step would be the elementary step, kind of behind the scenes, that takes the longest. Okay? So usually if you're dealing with mechanisms, what they'll say is fast, fast, slow. Or they'll say slow, fast, fast. Or they'll say fast, slow, fast. Okay, so the slow one actually is the one that's going to set your overall rate. Okay, your observed rate. Let's see, what else do we have on this slide? So your rate determining step, your slow step in a mechanism of elementary steps can be anywhere. Like I said, it can be at the front, slow, 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 fast, 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 okay, or it can be at the bottom. So you go fast, 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 slow. Now, if you're like me, kind of new to this material, like now, Mrs. Snipes, has it ever happened where you have 2 slow elementary steps and not in the problems we're working? Okay, so there'll only be 1 slow, and it will be rate determining of your overall reaction of interest. Okay. Reaction intermediate, D as in dog, was a reaction intermediate. We saw it when we kind of explained the termolecular process actually occurring in two bimolecular processes. So a reaction intermediate is kind of like the word intermediate might imply. It's kind of in between. I think of it as kind of fleeting. Okay, it doesn't show up in your overall reaction of interest. And it makes you want to go find D, doesn't it? It's like, well, I want to see D. D shows up somewhere, right? So sometimes you can find D. Sometimes you can isolate these intermediates, but sometimes you cannot. But your intermediates, like if you're just like we did a minute ago, if you're looking at a mechanism where you have a series of elementary steps and you're going to add them together to get your reaction of interest, if things cancel on both sides, then they're intermediates. If they don't show up on your reaction of interest at the bottom. They're like ghosts. Okay. So somehow, the reason this topic is important is we need to understand kind of the elementary steps, the script behind the scenes, in a way though that it needs to match with what we observe. So like what we see with our own two eyes as the reaction's occurring. So the mechanism, which is a series of elementary steps, need to be consistent with what we know about changing the molar concentration of the reactants and what happens to our rate. Needs to be consistent with the products we observe. Needs to be consistent with the rate law expression. If we sprinkle it with catalyst or inhibitor. Okay. So mechanisms is the script. Mechanism is telling you what's happening behind the scenes. With that in mind, I will tell you that sometimes a mechanism is just a single, sounds like an oxymoronic statement. Sometimes it's just one elementary step behind the scenes. You're like, oh really? That's pretty easy. So you take that elementary step, draw your line, redraw that elementary step again, and that's your reaction of interest basically. Which if your mind is fast forwarding, you're right. If your mechanism consists of only one elementary step, guess what? You get to use its molecularity as the reaction orders. Okay, so you're right about that. That's when stoichiometry will work fine, yeah. But, so, something to keep in mind. Yep. Okay. So, in my notes, I'll see if my notes kind of connect up with this. Seems like I'm missing a few slides. But we're going to look at one where basically we know the reaction of interest only has one elementary step. Okay? And it would look like this. Okay, we have N2O plus NO going to form products. Okay, so we have two reactants. Stoichiometry is one mole of N2O reacts with 1 mole of NO. Right. Now, this is where I'll just kind of do it on the slide. Since the mechanism consists of only one elementary step, we can use the molecularity to get to the overall rate law expression. So do you buy this? Quit. Go away. This is what I get. If we know that, if there's only one single step, we use molecularity like this. Rate is equal to the rate law constant K times N2O. So what's the reaction order of N2O? 1. Molar concentration of N2 raised to its reaction order, which would also be 1. Okay, so don't count on that though. Okay? Cool. And then I said that, don't worry too much about trying to get through all this because, to where I want to pretty much, because there's a bunch of slides that do this. All this is, you see the two reactants, You're gonna see an energy diagram here in a minute. Do you guys remember, I think I talked about, oh yeah, we talked about energy barriers, the activation energy required to overcome. So the top of that energy barrier, think of this transition state. Now if you're like me, sometimes I get transition state mixed up with intermediate, reaction intermediate. Transition state is kind of like you have the two reactants, in this case, they haven't quite gone down to form products yet. So the transition state is the top of the energy barrier.
So the stoichiometry only works for elementary mechanisms, but does it work for the
See,
elementary steps?
The word elementary mechanism doesn't work. So
Oh, yeah,
yeah,
elementary reaction
elementary steps.
steps.
Elementary steps.
So, but if a mechanism is all unimolecular, can you use it for each step?
Right. And,
Okay.
and the one that I picked on just a minute ago, this one actually, where we know it occurs by just a single elementary step, and so we used its molecularity to knock out the rate law expression. Usually there's going to be more than one elementary step. And kind of what you were saying, I think, was what you do is you come up with rate law expressions for each of the elementary steps using their molecularity. Is that what you said? Yeah. Yep. So this is showing how the reactants go through a transition state to go to form products. Same thing here. Okay, those are your two reactants going to form products. Okay, there are your two reactants again. There's your transition state. See what I mean? I just feel like I'm beating a dead horse here. Okay, but my favorite way to show this is on this energy diagram. So this is an energy diagram. Think along the y-axis is energy. Think along the x-axis is time. Okay, so basically you start with the two reactants. You're going to go to form products. And we talked about this activation energy. Okay, so that's your energy barrier that I've been talking about right here. Okay, notice up at the top you have your transition state. Okay, and then down over here we have products. Okay. All right. So this is more likely the case where you have, instead of a single elementary step, you're going to have two or more elementary steps behind the scenes, your script, that goes to make your reaction of interest. The first one we're going to look at is an initial slow step. So our slow means rate determining, and followed by a fast second step. So let's see what, yeah. So in this case, we have two reactants, H2 and ICL. Notice that the stoichiometry is 1 to 2. The second paragraph says experimental evidence indicates that the rate law expression for this reaction is first order for H2 and first order for ICL. So see how basically, based upon this paragraph, we can write this rate law expression because somebody told us that's what they observed. Kind of how you guys got your rate law, or excuse me, that's how you guys got your reaction orders. All right. So somehow we need to take that observed rate law, the reaction of interest, from the reaction of interest, and come up with a mechanism that makes sense. Well, here we go. And this gets hard to kind of explain. It usually goes something like this. Actually, you have homework that makes you come up with, this is a script here. This is our two elementary steps behind the scenes. You have homework that's making you come up with these elementary steps. Usually for your test, I give them to you and ask you to confirm that these elementary steps proposed make sense with what you observed. Okay? All right. So let's double check to make sure that if we add these two together, we get the reaction of interest. And we do. Are there any intermediates here? Anything? The HI, yep, I'm liking the HI. That looks like an intermediate, exactly. And do you see where we get the overall reaction of interest? I got 1H2. Okay, does that make sense? And I got this stuff over here. I'm buying all that. Now, before I go on to the next slide, so which elementary step is it that's forcing us to slow down? It's the first one, yep. So the first one, actually, I could write a rate law expression for both of these, but actually it's this guy that I'm most interested in. So if I call this step 1, do you see where I can say rate 1, and by rate 1 I mean from step 1. I can use molecularity. So what would be the reaction order of H2 from here? First order, yep. What would be the reaction order of ICL? Yep. Okay. So the way you prove it is I'll put equals, question mark, the observed. That second paragraph or whatever on the previous slide says this is what we observe for this reaction. Do you know what I'm saying? We observed it first order H2 and first order Cl. So this script is consistent with what we observed. That's it. And we can use molecularity on actually both of those steps because they're elementary steps. But we only really have to focus on the one that's rate determining, and the one that's rate determining is slow. So this is where actually when I start to work problems, I probably, you saw me put the little subscript 1. I think to me that's important because it matched up with that elementary step. I think that's important. Does that all? Okay. So your observed, OBS for observed, was given initially in the problem. Your observed rate law expression was what you get with the rate determining step. Okay. Smiley faces all around. All right. So energy diagram, right? This is an energy diagram for the one we just did, where you see actually 2 elementary steps. It's exciting because each elementary step has its own little hump. Okay? 2 elementary steps, 2 humps. And each hump's going to have its own energy barrier. So we said you can get the energy barriers by taking the reactants, going over, and going to the top of the energy. Okay? There's your intermediate. So the first activation energy looks like, I guess I'm going for the delta H of the first. There's your change in enthalpy for the first elementary step. Here's your change in enthalpy for your last elementary step. Those would be additive. Oh, goodness gracious. Here's your activation energy for the first elementary step. And here's your activation energy for the second elementary step. Which elementary step has the greater activation energy? It's the first or the second? The first. And that's not, how do I say that? That's not an accident. Your rate determining step have your highest energy barrier. Rate determining. Cool. All right. So again, looking at the same thing, I think that's kind of cool how you can get an enthalpy for the different elementary steps, and they add up to be the overall enthalpy. Okay. Well, that one was a little more straightforward than this one. This one actually has a catch to it. Again, now we're going to look at something that has 2 elementary steps, but let's see, initial slow. Is that it? That's, the other one was initially slow too, wasn't it? Initial slow and fast second step. Yeah. Like I said, on the test, I will probably give you the elementary steps, okay, and you have to say, well, is that consistent with an observed rate law expression? But for your homework, that's not the case. So here we go. NO2 plus CO goes to form NO plus CO2. And in looking at the overall reaction of interest, they actually come up with a rate law expression where it's second order with regard to NO2 and it's zero order with regard to CO. So you change the molar concentration of CO and it doesn't change your rate. Okay. So right away you can see that we don't have it doesn't happen in a single elementary step, because if it did, we could use the coefficients of 1 and 1 and get your, So a possible mechanism, and we're going to confirm that this is the case. Oh, sorry.
What was the rate on the, okay.
Yeah. Okay. Molar concentration of NO2 raised to the second power. Actually, this slide says what I just said. Okay. And maybe I put this in there just to show you, you can't use molecularity. You can't use the stoichiometric coefficients to be your reaction orders, because this is the reaction of interest. This is not an elementary step. So, okay. Well, let's look at a proposed mechanism. What if, and like I already kind of told you, what if we're going to have the slow one, and then we're going to go fast? This works. We'll go ahead and, do I draw a line? Yep. So obviously your elementary steps need to add up to be equal to your reaction of interest, and these do. Do we have any intermediates here?
One of the NO2s and the other's the NO3.
Yeah, it seems like one of the NO2s is also an intermediate this time, doesn't it? But the NO3, the species NO3, yep, intermediate for sure. So let's think through this. We can come up with little mini rate law expressions for these elementary steps. We're going to focus on the first one, right? Because it's slow. That's our rate determining. So we could knock out a K1, sorry, not a K1. We could come up with rate 1, meaning the rate for the first elementary step, and it's slow, is equal to, and I usually put K1 because it's the rate law constant for the first elementary step. And then what would the molar concentration of NO2 raised to what power? 2. Yep. Because it's bimolecular. The stoichiometric coefficient of 2 in front of that. Exactly. And is that the observed rate? Yeah. So you see how you've just kind of said, okay, this is the slow one, rate determining. Elementary step, I can use molecularity. Okay, so that is actually, you're done. But if you have this on the test, you need to somehow say, so this is consistent with what's observed. So the mechanism, which is the series of elementary steps, is consistent with what's observed. All right, yep. So we focus on the first elementary step. Rate 1 is equal to K1 times the molar concentration of NO2 raised to the second power. Because it's bimolecular, we can use molecularity since it's an elementary step. And then down here at the bottom, I kind of did something that I do in working my problems. I said, so your rate law expression according to that mechanism would be simply gotten from the rate determining step, the rate law constant K times the molar concentration of NO2 raised to the second power, because it's bimolecular. And here, the K in our rate law expression, overall rate law expression, is essentially equal to K1. Okay. This is the one where I'm like, well, now this adds a little bit of a twist to it. So we looked at two mechanisms, 2 reactions, where the mechanisms behind the scenes had slow, fast, slow, fast. Well, in this one, consists of an initial fast step, and the second elementary step is slow. So we're going to focus on the second elementary step to get our overall rate law expression. So here's our reaction of interest. Now, hopefully you're kind of looking at this and you're like, oh, it can't happen in one step because it'd be trimolecular, right? And the observed, wow, goodness, the observed overall rate law expression looks like this. And it's tempting to say, well, we could just use molecularity, right? NO raise the second power, BR2 raise the first power, okay? But don't do it, okay? Please don't do it. So how would you answer this question? Yeah.
Because it's unlikely for it to be triangular.
Yep, it's unlikely to get those three particles together. Yep. Okay, very good. So again, let's see if actually this works for us. These two elementary steps. So what's different about that first elementary step? What is that? What are the reaction arrows telling us? It's an equilibrium. That first fast one, it goes from left to right. Okay, that first elementary step, and it also goes from right back to left again. It's an equilibrium, fast. And actually we're going to use that to our advantage. So let's just double check, make sure they add up to be what it needs to be. Do we have any intermediates? Anything that shows up in an elementary step but it gets canceled out? Yep. What's our intermediate?
The NOBR2.
Yep, NOBR2. That is definitely an intermediate. Well, let's do like we've been doing, all right? Just for kicks. Let's pick on the slow one. Slow guy happens to be the second elementary step, and let's use molecularity to write a rate law expression. So I'm going to call this rate 2 is equal to K2, and then I'm going to use molecularity. Okay. So I'm going to write what? The molar concentration of NOBR2 raised to what? The second power, right? Or first power, excuse me, first power, times the molar concentration of NO, also raised to the first power. Okay? Now, a few things there. Right off the bat, you're like, well, now that doesn't match with what they told me was the observed. So that's a problem. And the other problem is if we stop here and make this our overall rate law expression, we actually have an intermediate in our rate law expression, and you can't have that. So I'm going to show you how to get rid of that, okay? And actually, it's going to fix our other problem. So if you run into this, this will not work. But there's hope. So somehow we need to make that intermediate in terms of something real. And our something real choices are, I'm going to cheat. Our something real choices are NO or BR2. NO or BR2. That NO BR2 has to go. Well, in a problem like this, where you have an intermediate in your slow rate determining step, there's always going to be a fast equilibrium before it. You can always use this. Okay. So let's look at that fast fast equilibrium, the first elementary step. So it goes from left to right, and it goes from right back to left again. I think I'm going to go ahead and kind of do this right here, because I'm not sure how my builds go. Okay. So NO plus BR2 goes this way to form. Now, I'm going to go ahead and just stop with that. It goes that way, right? I'm actually going to call this 1. I could go ahead and use molecularity to come out with rate 1 is equal to K1 times the molar concentration of NO raised to the first power using molecularity since it's an elementary step, times the molar concentration of Br2 also raised to the first power. Now, I'm going to go ahead and show its equilibrium part. I'm going to go back the other way. I'm going to call this -1. Does that work for you? I'm going to put a rate -1 is equal to, now I'm going back that way. This is my reactant. Okay? The molar, K -1 times the molar concentration of NOBr2, also raised to the first power. What do you think? Okay. So I got, it looks like a mess, but this says that the rate in the forward direction is equal to the rate in the reverse direction. That made my life a lot easier. So the rate in the forward direction, K1 NO, molar concentration Br2, is equal to the rate in the reverse direction, K -1 NO Br2. Okay, does that work for you? I think it works for me. That's the definition of what equilibrium means. The rates are equal. All right, this is my wild child. This needs to go away. Okay, so basically I'm going to solve for that guy. If I want to solve for that guy, I'm going to bring him over here because that's usually how we do this sort of thing. NOBr2 is equal to, I'll put this quantity divided by K -1. K1 over K -1 times the molar concentration of NO times the molar concentration of Br2. Do you buy that? Okay. Now I'm going to kind of catch up with my notes. So I've just basically done this, and I just kind of want to convince you of how this works. So the reason I did all of that was, of course, NOBr2 is my intermediate. NOBr2 is the thing that showed up in my, when I did my rate determining step, that's the quantity I need to get out of there. So now I can take the quantity up there, the K1 over K -1 times the molar concentration of NOBr2, and I can substitute it back in there, and by the way, I probably would do something like this. Oh, in my hand. I'd probably add a little subscript there. Do you guys recognize this is what we came up with? This is our rate 2 from our second elementary step. When I substitute that in, it looks like this. Combine my K's together. So I have K2, K1 over K -1, where those are the rate law constants for your second elementary step, first elementary step, in the forward direction, first elementary step, in the reverse direction. I bring down now my NOBr2 times NO. And of course, NOBr2 times NO. I guess I didn't. Yeah. I combine my NO terms, and of course now I get NO raised to the second power, which now actually I have arrived at what was observed. This actually, a few slides ago, was what the observed rate law expression was. We said it was second order with regard to NO and first order with regard to Br2. And I have, using the first elementary step, gotten rid of the intermediate and applied it to the rate determining step, the second one, and now have a rate law expression according to the script that matches what was observed. It's fun. Fun with algebra. Okay, so that's as far as I want to get, but then I'm gonna go ahead and make this assignment, because this is all stuff we're going to cover. That's easy enough. So this will be done Wednesday. Let's take a look. Let's see what my hints were. They're fun. There. So it's a lot of blah. If you're like me in this sort of problem, I have to read it several times. And if you read it a few times, you'll kind of extract out the important stuff. There's three elementary steps when you read it a few times. The first elementary step you get from 1425. The last elementary step was given in the context of the problem. This is one where actually you have to knock out the third elementary step. It's kind of like a subtraction addition problem. Okay, you should be able to do that. The middle step that you're going to come up with actually must be the slow step. So this is actually where you have 3 elementary steps. The second one is slow. That's the one you're going to come up with. And it needs to be consistent with the observed rate law expression. So not too bad, kind of fun. And it must cancel the intermediate N2, O2. So don't forget all 3 of those have to add up to be your reaction of interest. Kind of fun. It's like making chemistry as you go. So after you come up with your second elementary step, your slow one, then go ahead like we've been doing and prove that, well, if that's slow, I can use molecularity to come up with a rate law expression for that elementary step. You're going to have an intermediate in it, and you're going to get rid of the intermediate by using the first elementary step, just like we did in class. Okay, reaction of interest. If you read it a few times, you'll kind of come to this sort of thing where, again, not giving you the second elementary step, but you know the one step you have to add it to, and you know the reaction of interest. So you should be able to knock out that slow rate determining step. And those are my hints for that one.
So the reactant, or the product step will always be in the reactant step.
It seems like it.
Pretty
Yeah,
well for most
yeah. It'll be, but then you can also bring in other reactants that you have available too. But yes, definitely. Yep. And then 2 more. This one you're given even less, or propose a 2-step mechanism. 69 actually have the answers in the back here, or you have the answers for this. Okay. Yeah, there's a typo in this one. It really should just say rate is equal to K, not an extra equal sign. I'm not sure why they did that. Okay. Now, these, as I'm remembering kind of how you guys are all always into that extra credit stuff. I'll make the last 2 extra credit. The first 2 are for sure you should be able to do. And the last 2 will be extra credit, okay? Me too. So, any questions? Okay. Yay. That'll do it for today.